This next video is still on the translation of a certain point on two different lines. We have here the line L x minus 2y equals 4 and M x minus 2y equals negative 4. We have already graphed them in the Cartesian plane, carry over by the previous videos together with the identification of the intercepts that allowed us to graph that. At the same time, we're able to identify the unit normal vector for the normal line that is actually perpendicular to both of this. We'll be using them as we are going to determine the translation of point Z, 1 and 5, which can be found here. 1, 1, 2, 3, 4, 5. So Z is actually here. That's 1 and 5. So if we're going to translate that, we're talking about the double reflection of the said point, reflecting it on line M, so somewhere here, and then reflecting that on line N somewhere there. Cutting the middleman, this point here together with that line is actually the translation of the given point. Now, in order for us to move into this, we are going to use the formula that we have used before. Actually, there are two different ways to determine the translation of a certain point along two lines. We have the double reflection formula. You can actually take the first reflection of the point on the first line, and that said reflection take its reflection on the second line to get the translation. This time, allow me to use the other formula, which only allows us to identify a foot of the perpendicular pertaining on two different points on M and L. And at the same time, we are going to determine here the correct notation. The closest or the closer line to our point is M. So we are going to use this notation here. The reflection, okay, of the certain point Z on, the translation of point Z on line M, which would be the reflection of Z on line M, and its reflection would be again taken in charge or reflected along line L. Of course, there is also another way. We can of course come up with the reflection, okay, in this manner. But this pertains the reflection of Z to L. That would mean reflecting that to L and then reflecting such to M to get that, okay, to get the translation. But since the result of that would appear somewhere here, we did not translate the given point along M, okay? Because it should be translated along M. Hence, we're going to connect it to the concept that we are going to take its reflection on the closest line or translation along the closest line. So we'll be using again the first formula. We have your x plus twice p minus q. But since we are using point Z, so we can simply change this to point Z. Now, this would be the formula to determine the translation of Z along M, but we don't know the P and Q yet. P is actually the foot of perpendicular on the closest line M using a certain point Q on the other line L. The point here is that, okay, we're going to pick a certain point on, for this, it's the other way around. It's foot on L using M on Q and M, because it's M that is actually the closest line. So we're going to pick a certain point in M, anywhere here, of course, and you can even use the intercepts. If we're going to pick this point, its foot, the P value is somewhere here. Its corresponding point when we draw a perpendicular segment or line. So that would mean that for any Q point that you're going to pick, if you're going to pick this intercept, it's somewhere here. That would be our P. In short, our P is dependent on our Q. Now this time, we're going to determine what would be our Q first. Okay? So of course, we know that Z is actually the point 1 and 5. And we're going to solve its translation. So let's pick Q on M. Okay? Q because it's the closest line. So you could actually choose here any of these two. But just to be consistent, let me use here the x-intercept. You could always use the y-intercept as long as you will use the appropriate foot of perpendicular on that specific point. But allow me to use negative 4 and 0 as our Q. That would mean we can now solve for our P, which is the foot of the perpendicular, which is actually has the formula of x minus we have here the inner product of x minus p in the unit normal vector times the unit normal vector. We have here our unit normal vector. This is also indicated in the previous videos, and we are able to determine that using a normal vector over the length of that said vector. But we don't know the x is. At the same time, this p here might be problematic because we have used p for our general formula. So allow me to change this into specific, a more specific version. Instead of x, x is actually the point q. Okay? We're going to use point q as our reference for the foot. Again, in this case, that's our q, and you can choose any other point, even the y-intercept alone. So minus, you have q, minus, instead of p, a point on L, which is the foot, so that it will be disregarded. We will not be confused with the proper notation. Let me use the intercept that can be found on your line L. Okay, the intercept aside from P that should be found on L. Any other intercept that you can use there. Okay, take the inner product against the unit normal vector, and we have here the unit normal vector. So let's use this formula so that we will not be confused with this here. So to solve for the foot, right, we will have here your q, which is actually negative 4 and 0, minus, okay, still your q, negative 4 and 0, minus an intercept on L. Now again, it's up to you which intercept you will be using, but to be consistent, let me use this, and at the same time, the other purpose for that is when we try to use our q intercept, our intercept as 4 and 0, we would see a process in our formula that is actually easier to look at, because you would see that the two components, second components, are actually 0, and it's easier for us to manipulate such, okay, at the same time integrate it to the inner product, because the other part of inner product is a little bit complicated. You unit normal vector in this manner. Inner product of that times your your unit normal vector. Okay. Okay. Don't be concerned with the radical expressions. They will be removed later on. So simply continue this to solve for your foot. That's negative 4, 0. You have here, when you're combining that, okay, again, it's easier for us to do that. That's negative 8 and 0. And then you're going to take its inner product with the unit normal vector times the result. The result of that is actually a scalar. Okay, take note of that. The result of any inner product is a scalar quantity. So you have your negative 4 and 0. Inner product of this, since you have 0, take note, its inner product, you're going to multiply the components and add them. But the second result would be 0. So what you will have is the first result, negative 8 over square root of 5. Of course, plus 0 as the product of the next components. But since it's a 0, let me proceed with this. Times your unit normal vector now. Okay? This time, you would see that your foot, which is your P, is negative 4, 0. And you will have your minus. You're going to multiply that scalar quantity now. When you multiply that here, you will get a result of negative 8 over 5. Take note, square root of 5 and square root of 5 is 5. And the other one is positive 16 over 5. In short, your foot, which is actually our P, needed for this formula, not this one, not this one here, but this one here, right? So you will have to use negative 4 minus negative 8 fifths, okay? And then the other component is 0 minus 16 fifths, which will give us the result. You can use your calculators there. We have negative 4, that becomes plus, okay, 8 over 5, or 8 fifths. So you will have the result. By the way, it's negative 4, right? So let me try to review my process here. So it's actually in fraction form. You will have negative 12 fifths, and the other one is negative 16 fifths. So this is 5, not 15. Sorry for that. Okay, 16 fifths. So you could see that your point P, or the foot of the perpendicular, is actually in the third quadrant. Before we continue, let's try to have a review. Okay, take note that we chose this as our Q. So it's P, corresponding P. The foot of the perpendicular here is really on the third quadrant, and it's correct that the notations or the coordinates or the values for the abscissa and the ordinate is actually negative. Okay, now that is for our P. To finish this, alright, let me use my space here. Since we have our P, let's jump to this now. We have the reflection, or the reflection of your point Z along M and then L, or again, the translation of Z along M is actually indicated by your Z, okay? The value of your Z identified here as 1 and 5 plus twice. Let me simply write the formula first. So it's actually Z or X in general instances twice P minus Q. So Z is again, our Z is 1 and 5. 1 and 5. You have here plus twice. Your P is negative 12 fifths, then negative 16 fifths, minus your Q here is negative 4 and 0. Okay? This is still 1 and 5. So plus 2. Combining the two forms here, this will become negative 12 fifths plus 4, right? So you're going to try to come up with your calculators now. Plus 4, of course, in fraction form, that's actually 8 fifths. This is actually now a point. Let me use parentheses here. And for second, you have negative 16 minus 0 is still negative 16 fifths. So your translation is a result when we have 1 and 5 plus, of course, 2 times 8 is 16 fifths. You have minus 32 fifths, which will give us a result. 1 plus 16 fifths. 1 plus 16 fifths is actually identified as 21 fifths, okay, over 5. And the second component is 5 minus 32 fifths. You will have a result of negative 7 fifths. Okay? So you can of course verify this by double reflection, but let me also share to you another way of verification here. That's actually 21 fifths, or if I'm correct, that's 4.2, positive 4.2 and then negative 1.4, right? Okay? So again, 4.2 and negative 1.4. 4.2 is actually 1, 2, 1, 2, 3, 4, 4.2 and negative 4.2, it is 4, so 0.2 here and negative 1.4 somewhere here. This should be our the translation of your Z along, sorry for that, again let me rewrite this, the translation of your point Z along M, which is given as positive 21 fifths and negative 7 fifths. As you can see, it's in the fourth quadrant. Similar to this, if we're going to take its reflection here, it would be here. Take its reflection somewhere here as well. So basically, the point is really in the fourth quadrant. So this is how we take the translation of a certain point along two lines. Again, earlier, to make sure it's a translation, you pick the closest line. Then, in that point of view, you are going to identify correctly the P and Q, because P must be on the second line and Q, which must be on the closest line. Okay? Again, verify this using double reflection and I believe you will get the same answer. So this is how we do it for translation of a point along lines. Thank you very much for watching.